I'm really excited to introduce our first keynote speaker of the session. With our theme being, quote, can interconnects keep up with AI? It is really great to have a speaker like Mark, who has such a long history with AI, starting back to in the 90s when AI was really just starting out. He has pioneered a number of efforts in fields that we take for granted today, including distributed computing, cybersecurity, and cloud computing. At Microsoft, he is recognized as the primary or co-inventor of service-oriented architectures, service-oriented infrastructure, and service-level expectations, and he also helped to build out their first cloud data centers. From there, he moved to be the chief security officer at Expedia and later the same at GoDaddy. He is currently the chief technology officer at NeuralFabric, where their goal is to pioneer micro foundation models to decrease costs, ensure data sovereignty, and democratize AI. Mark, Mark loves the pace of development and evolution in AI, where every 4 to 6 months, the technology, the models, and the frameworks turn over completely. So it's a constant reinvention, keeps him on his toes. So without any further commentary, let me introduce Mark Baciak and his talk.
Oh, fantastic. Thank you for that introduction. Hopefully I can do it some justice. With that said, thanks everyone for attending. And as he said before, we live in a very interesting time. I've watched, lots of different things emerge and come and go from a technology perspective, from comp sci and also from the hardware perspective. The one thing that I can say is in the last, let's say a couple of years, it's been a massive explosion with the pace of development that we've seen in regards to this specific area and domain. I remember, it seems like every time we come up with something new, the pace of development would shrink. We went from 10 years to 5 years to 2 years, and now we're down to about every 4 or 6 months. So whatever your code base was, if it's 4 to 6 months old, you might as well throw it away because you're using, antiquated ideas and you're not basically state of the art. And that basically is really hard to keep up with. Not only that, but the number of people who are doing research in this space right now. So the papers that you have to read and how you have to keep up with it is very, very, very complex. So just to give everyone, obviously, I'm a CTO at a startup, which makes my life really fun, 100-hour plus weeks, but I have to devote 20 hours plus a week just to reading papers. And I read really quickly. So to spend 20 hours a week reading paper to stay on top of research is really fun. A lot of times these are archives papers, so you find that it's more marketing than it is substance. And a lot of times they leave out key details, so you can't really implement it. And they really don't show the proofs to some of the claims, but hey, that's the nature of the papers. But they give you rough ideas of what their invention is and kind of how it can be used. And then other ones go full bore. They give you full access. They give you GitHub repos. They really open the kimono, and that makes life kind of fun. So from a session perspective, we're going to look at a couple different things. So first, we're going to look at generative AI models in general. We're going to actually explore the basics of building a foundation model. Now, there's very few people on the planet who actually build foundation models. Everyone kind of talks about it, but it's kind of rarefied air. So I want to kind of, take away, that rarefication and realize that anybody can build a foundation model. And it's not really that hard to do once you have the basics. With that said, coming up with the frameworks and the pipelines for it is a little bit challenging, but you can get through that. Fine tuning, you just had a great conversation on fine tuning, as you probably saw before. And what we're going to go through there is what fine tuning looks like, how to fine tune a foundation model, and why are you doing that? What can you get from it, and what lessons are learned there? And finally, we get to the big one, which is inference. Well, you gotta, once you've created this model and you've now fine-tuned it, you got to make it generally available for the world. So what's it take to, and how do you look at running inference for these Gen AI models? And then the big part of this is, people looking at this and wanting to understand the space is decide what you like to focus on because the surface area is way too big. And, we really, you need to kind of dial in the space. And and I'll kind of go into some of the decision points, so it'll give you hopefully a roadmap or at least some ideas that you want to consider when you're going over your decision sets. So, of course, the neat thing about generative AI is you can use Gen AI to talk about AI. So that's exactly what I did. So a couple days ago, I said, "Hey, this is pretty easy. Let me go ask the latest generation of Grok that just got released." And I said, "Hey, create a picture of how to make a large language model." And so it was a pretty simple prompt, one in there. And for us in the cheap seats, I'll go ahead and expand it. And this is basically how Grok thinks that you should create a large language model. Now, there's a lot of technical terms here that even I don't understand, but it gives you a rough idea that, generative AI is definitely at just the start of its journey. And there's going to be a lot of things that are going to be needing to occur. Also, in the course of my talk, I'm going to be using certain terminology that you may or may not be familiar with. So, some of the words that I use might look like this. You've never seen them before or heard of them before, but just take it for there that it'll give an educational point or at least a base to start with. So let's look at the growth of LLM parameters and the size of these models from 2018 to 2024. We're basically just including all the major companies. Now, when we started and you go back to 2018, you had a couple different things out there. You had BERT from Google and you had GPT-2. And that was some pretty cool stuff. Google then came out with their T5. And then what really broke onto the scene was GPT-3. So GPT-3 was really our first blush was seeing something that we're like, wow, we can do some really cool stuff with that. And I know that in 2020 and 2021, when I was working at Microsoft, we had an internal project that I created called Teamworks, where we were actually using generative AI and ML to work on very hyper-specific business problems. And we saw some really good things when we coupled both of those things together. But again, those are really small, problem sets and areas that we were trying to solve. And that's why we got some pretty good results. But the industry continued. And GPT-3.5 then hit the scene and everyone went insane. The companies were coming out of the woodwork, and then you had this major explosion. So 2022, 2023 became like the Wild West. It reminded me of the days of cloud computing. It reminded me of the days of other technologies. Like let's go back to the 90s. This will date me a little bit. But if you could say that you had a .com, then investors would just throw dollars at you. They didn't care what the business model was, whether you would make money. Didn't really matter what the business problem was. As long as you said .com, you got dollars. Well, in 2022 and 2023, that's the same thing for generative AI. So as long as you come up with something and say that you were doing generative AI, people were basically willing to invest in you. Now, obviously, now people are starting to ask questions because it's been a couple of years and they're looking for the ROI on those investments. But these models continue to get larger. We've had now the release of GPT-4, and everyone's kind of guessing what that is. Everyone thinks that it's at least 1 trillion, parameters. It's probably closer to 2 or 2.7 trillion parameters if you read some of the Reddits from people who actually work there. But with that said, we can see this line is going to continue to grow over time, which means that the compute for it, if we start to then, let's just use, a linear curve on our log scale, and let's project out for a couple years. Well, this is important because when everyone here is designing something, especially if it's a chip, if an industry is changing every 4 to 6 months, you can't, it's very hard to actually come up, design a board, design a chip, and actually get that into production in 4 to 6 months. Typically, that process, if you're lucky, you're 18 months. Realistically, you're probably 3 years. So when you're looking at this, what are you designing for? Are you designing for, basically trying to do state of the art for 2024, and that's what you're kind of designed for? Or are you going to design for some of these larger, places when you're going to actually come to market? And when we're looking at this, we're going to get into the, 10 trillion, we're going to get into the 100 trillion, and there's a good probability there might be even models that are in the quadrillion of parameters. And I don't even want to even think about what that space looks like. And that's assuming that we also don't have any other material advancements or basically eureka moments that have the possibility of occurring and disrupting this entire curve and marketplace. So I want to caution everyone that those are some of the variables in play because this is now taking off and is new. So let's talk about and go into this a little bit more. So I'm going to kind of bucket this in some rough areas so that we can just use shall we say a bucketing of sizes. So let's take small models. So from anywhere from 1B to roughly 10 billion parameters, right? These are the things that you see a lot of people working on. So you see Mistral 7B, you see Llama from Meta, that has 7B, that has 8B. Obviously, that scales to 70B all the way up to 405B with their Llamas 3.1. But really small models are kind of there. If you look at what Apple's now introducing and some of the stuff that's going on there, those also fall into the small model category for 2024. Then we get into the medium models. Medium models are, it's still a very ripe space, and a lot of people are playing with this. And we're going to basically put this as going up into roughly about your 40 billion parameters, all the way up to about, give or take, about 600 billion parameters. Now, medium models, that's where you are really, to run those, you've got, quite a large memory that you're going to need. So, to put these at full precision, you're not looking at one card, you're probably looking at two GPUs based upon the memory of those GPUs. And that's actually how you're going to be hosting them. Then we go into the super large models. Well, this is where you get into the fun space, right? Now we're talking, greater than, a trillion tokens, or sorry, parameters, and moving all the way up to, close to roughly about 80 trillion tokens. Now, this is only made for a handful of companies and governments because it's the only people who can be quite candid afford these types of large models. But if we look at this extrapolation, we also have another curve, what I call you cannot afford it models. And there's multiple reasons for that. Even if you had the money to actually produce these models, you really can't afford it because you won't have access to the resources. You won't have the power, you won't have the water, you may not even have the compute necessary in order to make some of these models. So this is where there is also an opportunity, but really, I'll let Meta and some of the other presenters through the conference, kind of focus on the you can't afford it models, large models, and also talk about medium models. And I'm going to basically use the plurality of my time to talk about small models. So when you're looking at building a model, unlike the Grok one, I decided to use AI to come up and generate 5 little parts here. We start off with the notion of data collection. This is where, based upon who you are. So if you're Anthropic, if you're OpenAI, you're Meta or Google, you're scouring the internet. You're gathering as much data as you can to collect the data. If you're a smaller company, or organization, you probably don't have those types of resources. So you'll move over to Hugging Face or other places in order to gather your data. And then you're going to then curate the data because raw data coming in, well, that's really not usable by models. You have to do some cleansing of it. You have to do some formatting of it. You have to make sure it's the right type of data for the model that you're producing. Now, for this talk, we are going to be only talking about large language models, not multimodal, just to keep it easy. But the premises and the things I'm talking about are basically are applicable to either LLMs or multimodal models. The next thing that you do is now that you got your data, you have to do what we call pre-training. Pre-training is going through the steps where you basically take that curated data and then you're going to turn it into a foundation model. And like I said before, not a lot of people are making foundation models because it really is a mixture of art and science. It takes a lot of knowledge to actually do it and to do it correctly and to get the results that you would expect. And then we move into the fine tuning side. Fine tuning in 2024, I can't throw a stick and hit a company who's not saying that they have some proprietary way of doing fine tuning. And so when you look at talk to people in the VC community, and even when I still remember we have some of our pitches from a couple months ago, great conversations because the first question they ask is, okay, cool. So talk to us about RAG and fine tuning because that's what they're used to hearing. They had no clue that a company was going to come to them talking about, well, we do a lot as an organization, we do a lot more than that. But yeah, fine tuning apparently is really out there, as well as talking about inference. Inference is now taking that model and allowing it to have interaction capability. So this is basically where you're going to host the model, and basically, if you think about it, this is where the inputs and outputs come in from that model that you've now created, whether it's the foundation model or the fine-tuned variant. Now, typically, you don't want to communicate with the foundation model because it's really not, it's not kind of giving answers like you expect. That's why you want to kind of fine-tune it. But roughly speaking, these are kind of the 5 different steps that you have to look for and think about. So when you're looking at, possibilities of areas that you want to concentrate on, think about these 5 different areas. And to give you an example of an application today that is very, very cutting edge is from an organization called Clover AI. Now, these guys are one of the hottest organizations out there today. So what they have in their vision and what they've already done is amazing. So they've been able to not just have one model, basically out there. They have multiple foundation models. On top of those models, they have then thousands of basically adapters or fine-tuned variants that go on top of these foundation models that then coordinate into these AI agents that are then there to do very specific purposes. And then they have this thing that's called a Clover master agent. So the master agent goes in and basically tries to figure out what you're trying to solve, goes back in, knows how to basically, if you look at chain of thought, breaks it down into granular tasks, knows which AI system it needs to talk or speak to, knows which AI agent to go to that is basically trained for that scenario, goes through, aggregates all the data, and gives you something like that. The key takeaway here is that, when you're thinking about the application of the future and the application technically of the next 6 months, AI is the application, but it's not going to be a single model or a single fine-tuned variant of the model. It's going to be a myriad of models and fine-tuned variants of those models that are running to perform tasks in a collaborative manner. So the hosting of these from the inference side becomes very, very critical. You have to think about, are we going to host this on the edge on your phone, or are you going to host this up in a massive data center on the cloud, or is it doing sovereign data workloads where it has to go into a proprietary data center? But there's an example of an application and where we see this going. So hopefully this kind of grounds everyone here on what's going to be coming into play. So pre-training, let's talk about actually how to create or make a foundation model. Lots of stuff to go over here, but let's take it from data to intelligence. So you take in your raw data, you do a whole bunch of data cleaning there. You can do text extraction, deduplication, quality filtering, and so much more. Once you've got that, you've got your curated data set. Well, great, I've got the curated data set in whatever format I have. Now I have to then think about my tokenizer. Well, the tokenizer, you have a couple different ways of doing that. You can basically take a pre-trained tokenizer. So you can grab one from Mistral, from Llama, or the like from Meta, like their Llama 3 tokenizer, or you can then train your own. For an example, you can take like GPT-2, and then you can then look over your training corpus and then come up and then you get to control the vocabulary, size. You get to then use it on your training corpus so that you have 100% affinity between your tokenizer and what's going to be produced in your model. Now, there's pros and cons to everything that you do in here, and everything has a cost. Once you've got your tokenizer, then you take that and apply it to your data set and you create a token set. That token set is then fed into basically a program that then goes through and then takes that and then runs it across, how you'd find your hyperparameters to then produce a foundation model. And so this is the high level view of how to go from raw data to a foundation model. And as I was saying before, a lot of complexity here, and not a lot of people are doing this. So let's give you an example of a model that we built that we called NF Biomed. And this is a foundation model. So we basically took this from a whole bunch of different data. The date range of the data is from the 1800s all the way to today. It's from life sciences, healthcare, pharma. The format is text. It's basically 90 gigabytes compressed, roughly 36 million unique items. Using the Llama 3 tokenizer, we come up with roughly about 65 billion tokens that we can use in order to train this foundation model. Well, by using that tokenizer, we look on the right-hand side, and with what we get out of this, and this again is for a transformer-based foundation model, we come up with roughly 1.67 billion parameters for a model. It's roughly 6.22 gigabytes in memory and on disk. So when you're loading up this model, that's how much memory you're going to need unless you quantize it. The tensor type, we can work with any in our pipeline, but for this one we chose PyTorch, but we could have chosen JAX just as easily, safe tensors or whatever. For the dimensionality of it, we went with basically 700 or 1,792 dimensions, 16 attention heads, and 16 layers. It's not that big of a model, so from us, we've been working on the scalar laws of what the dimensionality needs to be on a per tokenizer type as you move between 1 to 10 billion parameters. And it's actually kind of neat because you'll learn a lot by doing it. Now, if we take that exact same data set and the only thing that we change out is the tokenizer, we see something a little bit different. Well, the GPT tokenizer gives us a little bit different information. All of a sudden, instead of being 65 billion tokens, we're roughly 61.4 billion tokens. We're like, okay, well, less tokens, but you're still producing the same model. It's the same data. It's got the same number of dimension, attention heads layer. What'll be different there? Is the model going to perform the same? What type of things can we expect there? Well, as we said before, everything that you do with the model matters. So let me talk about this. So when we look at the only two difference between this is the tokenizer and the number of GPUs. So what we want to do is compare the Llama 3 tokenizer to a GPT-2 custom tokenizer that was trained or created via that training corpus. So the first thing that you see on here is that the number of parameters is different. So the Llama 3 produces a 1.7 or 6.7 billion parameter model, but the GPT-2 produces a smaller model, only 1.51 billion parameters. The time it took to make it was roughly 657 compute hours for the GPT-2 tokenizer versus the 714.4 for the Llama 3. Now remember, these have all the same dimensionalities. The only thing that we're changing out here is the number of GPUs and the tokenizer. And when we look at this, we also see something else that's very interesting is the number, how much energy was used to make this model. So the GPT-2 model took roughly 400 kilowatts of power to make versus the 447 kilowatts to make the Llama 3 model. But again, that's for a pre-training run. And I don't know if there's a question or I heard something ding. I don't know what that means. Anybody?
No question. I'm looking at if anybody does have questions, by the way, put them into the Slack channel and we'll ask Mark at the end.
All right, fantastic. Let me go ahead and fast forward. So when you look at this, we actually have our own way that we actually do automated model evaluation, and we can then point it to any model. So we can put it to, OpenAI GPT 4.0. We can put it to Anthropic Sonnet. And for this one, we decided to do it for Anthropic Sonnet. And we basically want to look at a couple of the, how did it review the accuracy of our test cases? And when we looked at the input and we looked at the output, and then it basically gave us a score based upon accuracy, relevance, clarity, comprehension, and language use. And we gave it, it had to give us a rating from 0 to 10, with 10 being the best. And when we came up with it, what we saw was a couple of different things. First of all, that when you look at the TPS, or the tokens per second, the GPT-2 was processing a little bit faster. So when we were running inference, it was running a little bit quicker. We also noticed that it would take, and it's very marginal, but it took a little less, tokens to represent the input and output data. So the tokens per word average was roughly 1.32 for Llama 3 and 1.29 for GPT-2. Not a big difference, but it is significant, especially if you scale this across, millions of calls per day. But the total score. So the accuracy or the total score for the evaluation came out to be 40.52 for GPT-2. The Llama 3 scored better at 41.43. Now you got to ask yourself, okay, great, this is awesome. Is the customer willing to pay, for that increase in score? And also, is that score statistically relevant in a real world situation with respect to how they're going to use it? And so this is something that when you're designing a foundation model, the customers get to really help with the input here. But there's more to the story here. So let's review some of the telemetry data of this pre-training runs for each of the models. And you're going to find some interesting things here. And this is where, as people who are doing hardware, you have a tremendous opportunity. Obviously, there's things that we can do on the software side of this, but this is mostly a hardware problem. When we look at this, we look at the throughput for the tokens per second, right? So when we're looking at the, and again, if we look at this here, the reason why you see two different colors here is because that's part one, part two. Our batch broke, we basically stitched it together, and this basically ran across. So this is on 4 nodes, and this is on 2 nodes. So you're looking at roughly 32 GPUs versus 16 GPUs. Some of the cool things to take about here is you see that from a GPU utilization, we're always typically at 100% GPU utilization. When you see these different spikes occur throughout this space, those are checkpoints. So when you're creating a model, you're checkpointing it. And, at the end of the day, we allow our users to figure out what the frequency of that checkpointing is, because checkpointing, as you can see here, is expensive. With that said, you have to determine how often you want to checkpoint, because if you don't checkpoint and you have a catastrophic failure, you've lost everything up until there. You can always resume from a checkpoint, but like if you're in the middle of one and you haven't done that, then that's kind of, not so good. So for these, because we were running on the nodes, we did a high frequency checkpointing. In the real world, we wouldn't do that this much, but we also were doing this to help to elucidate where some of the bottlenecks were occurring. The other thing that you're seeing here is you add more nodes here, even though it says it's at 100% utilization across the board, you look at the power usage. Well, yeah, the 4 nodes, the 32 GPUs that are running over here are, they're having, first of all, a lot more variability. as far as the percentage goes, versus the 16, which seemed to be a steady state right about 90%. Obviously, they only dip on checkpoints. So, when you look at this, this is an area where, as people who are making chips, this is an area I would focus on. I'd be like, okay, and other people are going to be talking about this because I've seen the obviously the agenda, and people are trying to focus on how to solve this problem because, like I said, it is a hardware problem for communication. So when you look at this, though, the throughput or total tokens per second is actually a little bit different. So when we're up here, we're roughly, coming in at around 27,000 tokens per second. When we're down here, we're about 24, thousand tokens per second. So lots of throughput, but still not quite there. So it was kind of neat when you actually saw the comparison between there and the overhead that was actually applied on the models themselves. And again, this has been basically uniform so that we can actually do the comparison from a one-to-one part there. The temperatures were pretty consistent, so not a lot of data allocated there. Memory utilization, we were always tapping memory and tapping, there. It's the power one and the communication that are the two real, call outs for a place where I would focus on for an opportunity. Demos. Everyone says that you should never do a demo. But guess what? I like demos. So we're going to demo a couple different things. I'm going to quickly show you, this 1.5 billion parameter model in operation and give you a quick example of a tokenization. So let's go ahead and do this as we speak here. So here's our part. We have our 1.5 instruct, and we have it in two variants. We have it in 8-bit quantize, and we have it in full precision. So we'll start off with the easy one first. And this is a medical model. So we're like, hey, symptoms of COVID-19. Let me ask it a question. So I'm going to come through here and then ask it a quick question. Say, hey, based upon these symptoms, what could this be? And so when you look at it, it comes back and it's like, yep, it's definitely a respiratory infection. Definitely symptoms of the flu, COVID-19, and then it gives you, some more things that it could possibly be. Now, when you quantize a model, you're taking away some of its capabilities. You're taking away some of its intelligence. But the trade-off for it is lower memory field footprint and a higher number of tokens per second. Now, when I ask it this question again, and now we're going to do it on full precision, let's see what it comes up with. And this number should, first of all, it's going to be slower. And more importantly, it's going to give you a little bit different data. Now, the neat thing to note about this is that this was running at roughly, 67 tokens per second, and this is at 40 tokens per second. This is running natively on my MacBook M3. So you're seeing everything here run natively as an MLX. So we took advantage of the Apple hardware, and we've optimized as much as we could in order to produce this model. But there's a rough idea of seeing a model in operation, and also how you change precision, you actually get different details and you get more accurate details. So quantization, whilst it looks interesting, it also has some dangers to it because you're basically taking away what the model can do. We also talked about the tokenizer. Well, let's look at Llama 2 and let's put in this question. And if you notice, the tokens that came in from Llama 2, the tokenizer from Meta, it came in with 86 tokens for the representation of these 287 characters. Well, if we switch over to Llama 3, all of a sudden we see that it completely redoes the tokenization of that. So it reduces the number of tokens for the same number of characters, which then also decreases the amount of entropy or chaos that occurs in that foundation model creation. Because that basically means that you have less pathways to go and has a more firm understanding of those data and that concepts. So when you're basically looking at tokenization and you're putting in data, lower tokens for the same number or for the same type of data is a better thing. And even that small little difference has a huge meaning on what it takes to do in basically the creation of the model, its fine tuning, as well as its inference and how accurate it actually goes there. So there's a quick example of looking at, the model in play working locally, and also, a quick way to look at tokenization. Let me go ahead and head back to the model real fast. So um, there also are features you can add when you are in control of your foundation model. And like I said, every 4 to 6 months, something new comes out. So I still remember when basically, FA came out, FA2 came out, FA3 came out. And every time that, a new one comes out, you basically have to go through, rip out your old one, put in your new one, and then say, all right, cool, we got a new, something new here. Originally, we had DPO, now we moved to DTP. There's all types of different things that come into play. But the what we're trying to get to at this slide is when you look at the advanced model features, you have to look at the cost benefit ratio. So from a GQA, the whole purpose of it is it's supposed to make the model, your existing transformer based model, faster and smarter. That's the whole premise of what it's supposed to be doing. But let's talk about the cost versus benefit analysis. Because remember, nothing's for free. So this is kind of a neat one. So if you look at the throughput of on device on tokens per second, this is kind of wild. So what you find out here is that on a 1.5 billion, technically a 1.67 billion parameter model, what we found out very quickly is when we took everything, kept the parameters the same, everything the same. The one thing we did change was the number of layers because when you're using GQA, it's recommended to go basically deeper versus broader with respect to the layers. When we then did the computation, or then when we ran it, we found out something very important. The cost benefit ratio didn't seem to be quite there. So it was roughly 3.7 times the cost or the amount of time it would take to train the model just to add the GQA feature. We're like, okay, well, as long as it gives us a lot more accuracy, it might be worth it. So when we did that, we said, okay, well, first of all, we got a reduction from the base. And when we added GQA on there, it took it from 37 tokens per second down to 34 tokens per second. The accuracy score, or sorry, the total score that we had for the eval barely nudged up from 40.52 to 41.09. So the question is, do you think it's worth paying 3.7 times the amount of money to produce a model for that minor delta in the total score and also a reduction in the number of TPS? I don't know. Maybe for your customer it is, maybe it isn't. It's also important to note when you're looking at these new features and these designs, are your cards optimized for it? Do you actually, so if you're looking at an ASIC or you're looking at some other type of card, have you then put in optimizations for these new features? Or have you built in, or are you statically locked so that if something new like GQA comes about, all of a sudden the card that you created no longer can actually support those advanced features? So like I said, from a hardware design consideration and the pace of innovation, these are things that you guys have to think about from a design consideration. Moving over to fine tuning. Fine tuning is, I think that was kind of explained in the previous session, but I'll just quickly go over it again. This is where you take a foundation model. Technically, fine tuning, this will be kind of fun. You can actually fine tune on a fine tuned model. So fine tuning doesn't have to happen from a foundation model. We've actually taken a model and as an experiment, we actually kept on fine tuning it for different things. And we exceeded over 30 times fine tuning a model to look and bring out different characteristics. It was a really weird experiment, and the model kind of got wonky once we hit about 12. By the time we got to 30, we pretty much had destroyed the model, but we want to see how far we could go with it. But the premise here is you take a data set And you want to come up with something that you're trying to do there. So you take that data set, you take your tokenizer, you do your token set, and you put it up into your trainer. Now, once you have your trainer, you can do basically full precision. I wouldn't recommend doing that because that's super, super expensive. But hey, if you got the money and you think that it's worth it, go for it. Most people are using PEFT, or parameter efficient fine tuning. And of course, if you're using PEFT, no one just uses PEFT out of the box. They'll use something like LoRa, or more specifically, people are using QLoRa. The low rank adapter or adaptation, the difference there is one is basically quantized and the other isn't. And you can choose what the data type is that you're going to be doing for there. With that said, once you're done with that, then you actually have your fine-tuned model. Now, the fine-tuned model is kind of fun because you can do it for basically chat. When you look at if you just go down the SFT route or supervised fine-tuning, you're trying to fine-tune it for behaviors. So, or how you're going to interact with the model. For an example, this one happened to be instruct fine-tuning. So we basically had, 40, roughly 44,000 unique items that came out to 45 million tokens. We then fine-tuned the foundation model, and that's what you saw with NF Bioband. So it can then take in instructions and give you the right data back. When we look at the fine-tuning telemetry, I want to focus on a couple different things. And we wanted to show you this because this goes back to what we were saying before. If you look at this on a single box, right, a single CPU with 8 GPUs, we have this basically shown in the red where we have 8 H100, or I don't know what color that appears on your screen, but we have basically eight H100s. And you see here it works beautifully, super high precision. It's barely oscillating. It's taking in checkpoints, very well and super fast. Once we move that over to 2 nodes, all of a sudden, as we're doing checkpoints and we're doing our parts, we're watching that dip occur again. We also ran it on AMD for the MI300, and obviously the performance delta between an H100 and an MI300, there's a pretty large performance delta between the two. You can ask yourself, is this worth it for you? But hey, if it makes sense, go for it. There's also an opportunity here if people are looking to produce cards that also can do pre-training. You can also do fine-tuning with those same cards. But we want to then tease out this part right here, which is the 2 nodes, because we saw something that happened that was exactly the same. We looked at our GPU utilization. You watch your checkpoints come in, and we look at our power usage. Power usage was also, it also lowered. So power, when we looked at our power usage for over here, we were basically roughly at about 92, 93%. But once we went across 2 nodes, it never went above, it never even, it just went right under 80% for the power usage. So this is something that we're still exploring, but from a hardware perspective, you see it both for pre-training and for fine-tuning. So this is an area where I can't wait to see what you guys come up with as a way of solving this problem. Inference. Well, inference is, how do we run these Gen AI models, right? Let me give you an example here. This one's kind of neat. So when we're taking, let's say the PubMed data that's out there, you can get, from, a couple different places. You can get it directly from PubMed. They used to get it from the pile. But let's compare 2 different models here using the exact same data corpus or training corpus, right? So if you look at it, it's roughly about 35.8 billion tokens. And when Stanford created their Biomed LM model, and then they published the paper for it on the 27th of March of this year, it took them and they exploded it out to roughly 2.7 billion parameters. And they were using PyTorch, and it has a size in memory and on disk of 10.7 gigabytes. What we ended up doing is doing that exact same part, but we produced a 500 million parameter model, foundation model, got it down to 2 gigs. We then made it run across a whole bunch of different tensor types, and we wanted to see what the performance difference would look like. And we also wanted to see, based upon what we came up with, What would be the difference there? So if you look at the NF Foundation model pipeline comparison, then looking what the basically Stanford had done, it took them roughly 19,200 compute hours on an A100 to produce their model. They estimated their cost to be roughly $100,000 to make that foundation model. And again, you're kind of go back in time a little bit because that model was technically produced in 2023 and it was done with a team of scientists and researchers, and that not including the cost. This is just how much it costs to actually do the training run. Fast forward to today and using our pipeline, we were actually able to make that exact same model for $626.58. We did it in runtime of 0.71 days on 8 GPUs. And then to fine tune it, it took us roughly 6 minutes to fine tune it for a cost of $275. So today we can make that exact same model, much lower space, same, actually even a little bit better fidelity than they were getting out of it for a total cost of $630 versus $100,000. So you can see how the game is now changing. And software and hardware are now pushing forward. That's giving us, as as the from a science perspective, more gears and levers so that we can really push the envelope, and then make models at a much more effective price point. And just to show you, we were proud of this at the time. This is going back in the April timeframe before Apple did the announcement. You can actually see this running on two different parts. You see this running on a Vision Pro, which is to your right. And on the left, we have it running natively on, all these are all on full precision. And on your left, you have the iPhone 15 Pro and your Vision Pro. So we were pretty happy about it because, like I said, we got the models up there working. The Vision Pro is a little more complex to do. But we were just kind of saying, hey, could we take this and run this at full precision? And you notice our token per seconds, we're actually getting some pretty good results. So we can run these now completely disconnected and now offer new opportunities that didn't exist before. So also as hardware people, you have to think, what devices am I going to be targeting? And and when I'm looking at the marketplace, there's a huge area here that's an untapped market that I think everyone's going to be funneling into. And just to give you the rough numbers on here, that's our performance for the model as we moved across the ecosystem. So the Vision Pro, we're getting roughly 24 tokens per second, iPhone 19, when we iPad 38, and when we throw it on an M3 Max with the GPU, we were getting over 140 tokens per second. Running that on an A100, we were getting 22 TPS for the Biomed model and 220 tokens per second for the NF Biomed model. Now, another thing that you have to think about if you're looking at doing fine tuning or creating your own model, what are the pros and cons of taking someone else's model and then running with it, right? Well, first of all, most models today are generalists. They're not specialists. They also, because they're generalists, they also are more prone to hallucinations versus focusing on the area you like them to be a part of. The second thing you have to worry about is IP pollution. You have no clue where they got this data from. Meta doesn't publish where they got their data from. Anthropic, OpenAI, they don't publish where they got their data from. There's a multitude of reasons for this, and you can basically take your guesses why. My guess would be most likely copyright reasons, but you can go ahead and roll the dice on why you think they don't want to expose where their data came from. But there's also no way of knowing what's in there. What happens if they have bioweapons in there? What if they have the knowledge about things you don't want them to have knowledge of? So not knowing what's in that and these models is also a huge potential for your brand and reputation risk. It also means that because these models now have this inherent knowledge in them, you have to produce what's called guardrails. So guardrails are the ability of saying, okay, cool, you're asking for something, but I'm not going to tell it to you. Even though I have the capability to and probably have the knowledge, you really shouldn't be asking that question. Versus having a custom model, if it's not trained on it, it has no clue how to even answer that question. And obviously, if you're fine-tuning a training model and it already has that knowledge set in there, you can never, by fine-tuning, remove what it has learned, or has the abilities to do. So once it's baked into the model, it's done. You'd have to throw away the model and then clean it in order to get rid of that. And because the capital investments in these models are so large, no one's going to do that. And of course, it takes big iron to produce these versus commodity hardware to make a custom model. So let me do a quick demo on a generalist versus a specialist. So we're going to move over real fast to here. And at the top, I have a couple models loaded up, right? I've got our NF Biomed 05. I've got the Stanford model. I've got Mistral 7B, Llama 3B Instruct, and Phi 3. So asking a quick question, who are you? Llama and Mistral came back as very interesting ones. Phi 3 got it right. But both the Stanford model and Biomed model, because they're domain specialists, they really don't actually have access to this information. So they don't have any clue about this. But what happens if we ask it a question that's not medically related? And this is where we got our first little aha moment. So we said, okay, what's the single, a game scoring record in an NBA game? First of all, as you can see here, we're definitely pretty quick. But we have no clue what it is. We don't know what an NBA game is. We don't know how to do it. So we really don't know. But the Biomed LM had some knowledge of the scoring. It's like, yep, 100 points for each of 2 games. And then sure enough, if you look at the Mistral Llama, it comes back that it was Wilt Chamberlain who got 100 points in March 2nd of 1962. Moving over, got it right. Phi 3, so close. It got the person, it got the date, but it missed it and it had it at 105 points. And it also gave different answers. So I thought it was kind of interesting. So this gives you a rough idea of guardrails. If you're an enterprise, do you want your people to have knowledge of this? And why are you paying for a model that has data inside of it? Let's go and ask a more explosive question that you would typically guardrail and say, hey, what are the ingredients of the explosive TNT? Of course, we really don't know what that is. We're not trained on it. But guess what? Biomed LM actually had some knowledge of what TNT was. And that's because we got our information directly from PubMed. They actually got their information from the pile. The pile, and we're suspecting, actually had some incorrect information or other information that was not filtered out and including in their training corpus that was outside of just PubMed data, hence the reason why they would have knowledge of this. And of course, as you go across these, they're going to nail it 100% because there's no guardrails on these models for us. But that's great. Let me move over to a top of the line model from Anthropic. And of course, I'm going to ask a basic question. And this is talking about guardrails. Oh, by the way, there's a $15,000 bounty if you have a generic way of trying to bypass their guardrails. And of course, if you ask it the question, hey, what are the ingredients of the explosive TNT? Explain in detail how to make it. You're not going to get close, right? Because if you think about it, because they have guardrails in there, but the real question is, if they didn't have the guardrails, do you think that it knows how to do it? And of course, remember, there is a bounty out there that says, hey, if you can figure out how to do this in a generic way, well, what if there is a generic way to bypass all their guardrails? So just by doing some neat little stuff, the first one is the normal response it'll tell you. And then when we come up into it, all of a sudden, we have now completely bypassed our guardrails. So not only is it going to tell us what TNT is, it's going to tell us exactly how to synthesize it. No bueno. These are things that you really, really do not want out there. And like I said, and imagine you're in a corporate environment and someone's sitting there and just to, or you have someone who's trying to interface with your website and you have an agent out there and like, haha, this would be kind of funny if I actually did this. And with guardrails, out there, obviously, the model's going to say, nope, I'm not going to do that. But if you bypass the guardrails, it understands this, can easily do this. And imagine someone doing this and what that does to your brand. Imagine you're Nike, imagine you're whomever, and then you just put this out there and running in your enterprise. So probably not a good thing to do. So the premise here is that a lot of work needs to be done on models and curation because you have to be very careful of the capabilities and how they emerge. The last thing I want to move to as we move on through here is quickly talking about some of the things to look for with these models. So one of the things that we use is VLLM for basically inference and putting up these models. It gives us a lot higher, throughput, and when we put it up there, we're really happy with what we've done with it. But with that said, it didn't quite work for us because we were making our own foundation models, which means that guess what? There's a couple rules that we had to do. First of all, we had to go into and redo a few things. So we had to look at the heads that were supported. And if you look at basically the formula for this, its head size is congruent to 0 modulus 16. So in other words, basically, we're looking for multiples of 16 to do there. But if you want it to be uniform across a wider variant, really, you're looking for multitudes of 32, but 64 is the max number that we actually choose to go with because that allows us now to natively run on MLX, VLLM, and do quantization. So when you're designing your model and you're coming up with the hyperparameters, you're putting out what some of the dimensionalities should be, well, it's important. You also have to make the ability to, make the improvement. So not only did we have to make the changes to what we did for the VLM source code, we also had to do it to the respective CUDA files in order to support this.
So Mark, we've got about 5 minutes.
Yes, I'm getting right there. We're almost done.
Okay, all good.
So decide where do you want to focus on? So for example, D-Matrix, they decided to focus on inference hardware. So they're making hardware that makes inference better. So they're making it more economical from the number of basically tops and the cost per watt to produce those. We have other companies like Giga.io that we worked with, and they're basically taking away the complexity of basically the addressability of a single CPU to GPUs. So instead of having the limitation of 8 GPUs for CPU, we can actually now go all the way up to 128 GPUs using this architecture. Now, in full transparency, we actually are a partner with Giga.io. We love this technology, and we didn't show any of the results that's here, but we use this internally for our own needs. So that way we get all the benefits of what they provide, and this is how they were basically focusing on and solving this challenge. But the AI accelerator landscape is a complicated space. And because it's such a new space, everyone's trying to come up with their own term for the same thing. An NPU, a TPU, an LPU, an IPU, a neural engine, or even Trainium. So everyone's coming up with their own way of describing the same thing. So hopefully this gives everyone here some examples of what you need to look for, a holistic view of all the different parts, and maybe some areas that you want to focus on for the size of models and device parts and where you want to put them. So with that said, I will go ahead and stop the share and take a question or two.
Fantastic. Really, really interesting, Mark. Thank you so much. There's a question in the chat room. If anybody else has questions, please add them into chat. Matthew has asked, given your background and how you see the change, what advancements do you expect to see? Granted, the time pace is changing every 6 months, but in the next 5 or 10 years, what major advancements do you expect to see?
Well, again, this is all state of the art, and I'm looking at two major disruptive changes to happen. The research has already been published out there. It just needs to be gone forward a little bit more. Obviously, when you're looking at generative AI, you have state-based models, you have transformer-based models. These are different architectures that provide pros and cons in order to come up with that generative AI side. With that said, they're all still using the same data types. And one of the advancements that was made recently, and this was basically over a year ago, is people then took the data type from FP16 and BrainFloat 16 down to FP8. And FP8 was basically done by both AMD and NVIDIA. And what they did differently there is on forward and backward passing is they would actually change the exponent and the mantissa size based upon whether it was going forward, backwards, and propagation, so they could get more data in there. So you get more precision with a data type, and you get a lot of performance increases there. But remember, that's for one of those data types. In the future, I'm not going to say what it is, but I expect there's going to be a new data type that's out there that's going to basically take all this stuff and put it to the side. I've already got some preliminary, so I
Interesting.
said papers from it. But if that actually comes to pass, then you're going to see models that are going to basically be training orders of magnitude faster. They're going to be orders of magnitude smaller, and they're going to be able to basically not have to do a lot of the complexities that we actually do today. For an example, the matrix multiplications and all that other great stuff all will go away, and they will just be doing dot products, which is just addition. And because of
Fantastic.
that data type, it's going to really change the game if it actually then proves out.
Well, really, really good. And thank you so much for your presentation. If anybody has questions, the chat room will stay up. Mark, if you can log into the chat room on Slack, and you can answer some of the questions that invariably will come up.
Oh yeah, definitely would do that. And also, I put a little Easter egg in here. If you notice, my my photo is different from my actual face. That was an AI advanced version of me. There's a lot of difference between this face and the AI one, and there are 17 different differences there. I want to see if who can come up with as many of those differences. That was
Excellent.
one thing of playing around with AI.
That's great. Thank you. Now we get a contest too. That's great. Thank you, Mark.
All right, thank you very much.